into a rocket, because when I light it, the gases will expand because there's heat generated by that reaction. It's a very strongly exothermic reaction, and they will expand, therefore they will come out there, and that will make the rocket go that way. I've aimed it to try and hit the basket there. We'll see how good my aim is. So, 5, 4, 3, 2, 1. Oops. No, needs to be a bit higher. Right. Important message about science. Important message about science is, if you get a reaction to work, you don't know, you can't truly trust your result. You can only truly trust your result when you show that your experiment is reproducible, which means you do the same thing and get the same thing happening twice. Then you can trust your result. So that's what we'll do. Be good scientists, check our reproducibility. 5, 4, 3, 2, 1. Oh, nearly. Oh, no, nearly. But okay, let's try that side now then. So this is a little bit, the actual rocket is all about physics, but the energy is coming from chemistry. It's coming from hydrogen plus oxygen. That's what's giving you the heat, which is giving you the thrust. 5, 4, 3, 2, 1. Oh. Right. Okay, nobody died. That's good. So hydrogen, fantastic potential as a fuel. We can get energy, we can make things move. The problem, what we currently use as fuels is things like petrol and diesel and all that. The great advantage they have, 10 minutes, is that it? Bloody hell. Yeah, we started late. Yeah. The great advantage they have is that they are liquids. So let's just think about liquid fuels. The great advantage of liquids is that you've got lots of molecules in a small volume. They take up much less room. Remember, what you learnt over there was gases take up much more room than liquids. So it's great to have liquid fuels because you can just use a few milliliters of liquid fuels. In this case, we've got alcohols as fuels. The great advantage of them over petrol and diesel is that we can regenerate them. We can make them. We can make them via photosynthesis, or we can make them via chemical processes from CO2. We know how to do that. So we're not going to run out of liquid fuels because we have chemistry. Right. So lots of space, lots of energy available from liquid fuels. This is now a rocket. Like that, right. That's because I had some boron in it as well. Right. So, if we've got like 10 minutes, I think we'll just have to cut to the most spectacular. We've seen some green flashes, so let's have some blue flashes. The reaction here is not with oxygen. In the tube is NO, nitric oxide, NO. I've just put the fuel in, got an unusual fuel as well. It's carbon disulfide, like carbon dioxide, but slightly different. Let's see if we can react the carbon disulfide with the NO. Now that's what happens when you've got slightly too much or too little. Not entirely sure which. And because that small one's unreliable, I brought a bigger one. So, big tube full of NO, nitric oxide, which is actually quite violent to react with oxygen in the air. If you look carefully, when I take the top off, you'll get a puff of brown. There it goes. But we don't want that. That's NO2. And we need to mix up the fuel with the oxidant, and we also need to use the water to dissolve the NO2, thereby making nitric acid. But the main thing is we have CS2 and NO, and we've got a slightly bigger one. There's no guarantees in this world, but let's see if this one works. That's what it should have done. Yeah. Yeah. And the product of that reaction is sulfur. And so, you see what happens when we scale it up again? Right, so, yeah, that often happens. Right. Okay, so this is actually called the barking dog reaction, although the noise didn't sound much like a barking dog. That's where the little one works. Right, so let's see. Yeah. Now, that did used to be used as a photographic flash in the early days of photography, but I'm going to cut now to the most useful reaction that you'll see. We're going to do some engineering, because I've got two bits of iron that I want to weld together.